In this lesson, we can now finally, formally, put down the equation. Integral around a closed path, b dot ds will equal mu naught I net, and really you should add the word enclosed here, so put a little ENC in there. So enclosed, make sure you get that in there, is Ampere's law. So that is like when we had Gauss's law, integral E dot dA, n hat dA equals Q enclosed over epsilon naught. We could always calculate the answer to the integral using Q enclosed over epsilon naught. Now we can always calculate the answer to our line integral here by calculating that bracketed term, mu naught I net. And we have the convention that you have to use. So please, based on our electric field and magnetic field conventions we are using, the loop, when you ever use Ampere's law, has to go counterclockwise, and the ds then is part of that loop. And the current out of the paper is going to be positive. Current into the paper is going to be negative, always. Well, there are basically two versions of Ampere's law, one with symmetry and one without symmetry. Well, let's look at the no symmetry case first, because as I have here, the no symmetry case really is not of much help in terms of what we can understand physically, because the integral itself, b dot ds, does not really have physical meaning in the same way that flux, like electric flux, had physical meaning. So we don't really attach meaning to it, but I do want you to be able to get the answer correct on a test, or the AP test specifically. If you were asked to evaluate that integral over a closed path, you would do as we did on our last page of notes, look at the currents that are enclosed only. So you will not look at the currents that are outside, so we don't look at this at all. So that's outside, so that we don't use. Currents that are coming out of the paper are positive, so currents that are coming out are positive, and currents that are going into the paper are negative. So make sure you get your positives and your negatives correctly into your I net enclosed, and that's it. You'll multiply by mu naught, which is 4 pi times 10 to the minus 7, not something you have to memorize. So to evaluate the integral, very helpful. In terms of physical interpretation, we will not use it for really physical interpretation. So no symmetry was not much help. Symmetry, much help. Why much help? Well, we can very easily, very quickly employ Ampere's law to get a derivation for the B field for the long straight wire, and that's what this example here is showing. So I would like you to add to your notes that what we have here with the example for symmetry is the derivation. So derivation for B equals mu naught I on 2 pi r for the long straight wire. So if you were asked to do the derivation, this is what you would do. You would simply put a long straight wire coming out of the paper. Check. Put your Amperian loop symmetrically as a closed circular path loop around the wire that will automatically match the B field, which we know is circles around wires. We get cosine of 0 between the B field and the ds direction, so counterclockwise, cosine of 0. There is only one current enclosed. Out of the paper is positive, so I net enclosed is just I. B, by symmetry, constant comes out of the integral. Constant, and put here constant B by symmetry. All right. Comes out, the integral of ds is 2 pi r, and voila, we have B equals mu naught I over 2 pi r. We have started with Ampere's law, and in 2 steps, we got our answer. So this is just algebra to get it in terms of B. But you absolutely will be responsible both for our test or the AP test to be able to use Ampere's law to derive the expression for the long straight wire. So we now can definitely start doing some homework problems with Ampere's law, and hopefully that is now crystal clear.